Io is one of the most curious objects in our solar system. The innermost of Jupiter's big moons, it has plenty of features that set it apart from anything else that we have ever seen, including volcanoes, aurora, and a sulphur atmosphere. I'm Alex McColgan and you're watching Astrum, and together we will go through everything you could want to know about the hellish world of Io. Let's get to know the context of Io a little better. Jupiter has 79 moons that we know of so far. There's a few that orbit close to the planet, in and around the planet's rings. Beyond that are 4 large moons, known as the Galilean moons, named after Galileo, who discovered them in 1610. From innermost to outermost, these moons are Io, Europa, Ganymede and Callisto. Beyond them are the irregular moons of Jupiter, all of which are much further out than the previous moons. Io orbits very close to Jupiter, only 350,000 kilometers above Jupiter's cloud tops. This means from Io's surface, Jupiter would appear 39 times bigger in the sky than our moon. Io orbits Jupiter in only 42.5 hours compared to our moon's monthly orbit. Its orbit is actually in sync with 2 of the other Galilean moons. It orbits twice for every orbit of Europa, and 4 times for every orbit of Ganymede. This is what we call an orbital resonance. Orbital resonances greatly enhance the mutual gravitational influence of the moons, which means the gravitational forces from the other moons cause the orbit of Io to have a little more eccentricity than it otherwise would have. This is likely the primary heat source for most of its geological activity, as Jupiter's gravity pulls and tugs on Io, causing tidal heating. At some points in its orbit, the tidal bulge on Io is thought to be up to 100 meters. This effect is similar to what we see on Earth with the ocean's tides being caused by the moon, although on Earth the effect is much more minimal, the tides only usually shifting about 2 meters from high to low. Io is getting 300% more tidal force exerted on it in comparison to our moon on us because of its close proximity to the biggest planet in the solar system, Jupiter, and the other big moons in the system don't allow the moon's orbit to be any less eccentric, meaning Io isn't going to be getting any respite anytime soon. A day on Io is the same as its orbital rotation, which means that Io is tidally locked to Jupiter. Just like we can only see one face of our moon from Earth, only one face of Io can ever be seen from Jupiter. Io is a pretty big moon, although it is the second smallest out of the Galilean moons. It is comparable in size to Earth's moon and shares a similar density, meaning it has a similar amount of gravity. But interestingly, it does have the highest density of any other moon in the solar system, one of its many unique features. Another is that it is composed of mainly silicate rock and iron, similar to the terrestrial planets and our moon. In comparison to most other big moons in the solar system, which are made of water ice and silicates. Io in fact has the least amount of water of any known body in the solar system. Its core is likely to be made of iron or iron sulfides, surrounded by a silicate-rich mantle and crust. The core is not thought to be convecting though, as no magnetosphere has been detected around the moon. The mantle is thought to be liquid near the crust, and is at least 50 kilometers thick. This is where all the volcanism originates. Which brings us to perhaps the most interesting part about Io, the hundreds of huge volcanoes all over its surface. Before the 1970s, we didn't know much about Io at all, although telescopes were starting to pick up hints that the moon was devoid of water and that it may have a surface of sulphur. The first mission to see Io in any kind of detail was Pioneer 11, although the quality was still not great. What it did detect, however, is that Io was made of silicate rock and not water ice, and that it has a thin atmosphere. Pioneer 10 was also meant to take some close-up shots of Io, but this was lost due to Jupiter's radiation interfering with the onboard command system. the radiation Pioneer 10 went through was 10,000 times stronger than the maximum radiation around the Earth. The next missions to Jupiter were the Voyager 1 and 2 missions in 1979. Voyager 1 flew by at a distance of only 20,000 kilometers and was able to take some impressive close-ups of Io's surface. What it saw was a remarkable landscape full of vibrant colors and a total absence of impact craters. It found mountains taller than Everest, as well as volcanic pits hundreds of kilometers wide, and what looked to be lava flows. Most notably, however, was the presence of plumes coming from the surface. This proved that Io is volcanically active, and it is still the first and only place this has been visibly seen beyond Earth, not including cryovolcanoes. Voyager 1 also confirmed that the surface of Io is covered in different sulphur frosts. This is what gives Io its many spectacular colors. It found that it is these sulfur compounds that dominate the atmosphere. Voyager 2 also saw Io in July of 1979, but was much further away at 1 million kilometers, although it still saw 7 of the 9 plumes Voyager 1 saw in March, which meant those volcanoes had likely remained active throughout those 4 months. The really interesting images came about with the Galileo spacecraft that arrived at Jupiter in 1995. The spacecraft wasn't especially designed to study Io, but it was able to acquire some of the highest resolution images we now have of its surface. Sadly though, Galileo never worked at full capacity, as it had quite a few mechanical malfunctions, which means we could have had even better images had it been fully operational. What it was able to see though were plumes from many volcanoes, as well as confirming the volcanoes were erupting sulphur and silicate magmas, similar to what we have on Earth, except the magma on Io is also rich in magnesium. The surface of Io is spectacularly colourful. The yellow plains are composed of mainly sulphur. The white areas are mainly fresh sulphur dioxide frosts. Towards the poles, the sulphur is damaged by radiation, which can be seen as the poles appear redder than the rest of the planet. In other places, the colours of red are the deposits left by volcanic plumes that reached hundreds of kilometers above Io. The most obvious deposit is from the volcano Pele. Sadly, an inactive volcano when Galileo was around, but Voyager 1 was able to see a massive plume when it passed by. In this image, this plume is 300 kilometers tall and 1,200 kilometers wide. In other words, roughly the size of Alaska. Interestingly though, the source of lava flows on Earth are typically the depression you would normally see at the top of volcanoes, but these depressions are not found on high peaks on Io. Instead, you have these lava lakes with high walls along the outside. Here is Loki, the largest volcano depression on Io, 200 kilometers in diameter. These lakes are directly connected to the lava reservoir below, but usually have a thin layer of solidified crust on top. On average, Loki produces 25% of the average heat output of Io, but sometimes the crust on the lava lake sinks back into the lake, causing Loki to produce 10 times more heat than normal. This can especially be seen in one of Io's other big volcanoes, Shrivastava. Normally this area looks like this, but here the crust is seen falling into the lava lake. In this image where there is just white, the radiant energy from the lava curtain was so intense that the camera only registered white. In 2007, New Horizons used Jupiter as a gravity assist on its way to Pluto. It also used the opportunity to test its equipment. It focused its lens on Io during its flyby, and what it saw was amazing. Shrivastava, the volcano I just mentioned, was in full eruption, and the plume could be seen hundreds of kilometers above Io's surface. You can also see smaller eruptions around the moon. I must admit this is one of the most impressive things I've ever seen of space. Even though the volcanoes tend to be flat, it also has some extremely tall mountains, the highest one reaching 18 kilometers tall. These mountains tend to be completely by themselves, not as part of a ridge or a range. Although most are not volcanoes, lava lakes are found near them, indicating there are faults in the crust near these mountains. Another of the unique aspects of Io is its interaction with the magnetic field of Jupiter. Jupiter has an extremely large and strong magnetic field, and Io orbits within some of the strongest sections. The unusual thing about this interaction is that when particles from some of Io's thin atmosphere and its eruptions are lost to space, these particles float in orbit around Jupiter in what is known as a neutral cloud. This cloud can extend far beyond and behind the orbit of Io, but also surrounding Jupiter is something known as a plasma torus, a donut of ionized particles that follows the rotation of Jupiter's magnetic field. The plasma torus rotates a lot faster than Io's orbit, at 70 kilometers a second compared to Io's 17 kilometers a second orbital velocity. Io orbits right through the middle of it, with the particles from the torus bombarding the particles in the neutral cloud, exciting them to higher energies. These newly ionized particles feed into the torus, attracted by the magnetic field lines of the magnetosphere. These particles are lost from the neutral cloud into the plasma torus at a rate of about 1 ton of matter per second, which greatly increases the size of Jupiter's magnetic field. In fact, if it was visible, Jupiter's magnetosphere would be about the same size as the Moon in our sky. Io's interaction with Jupiter doesn't end there. Jupiter's magnetic field lines, which Io crosses, couple Io's atmosphere and neutral cloud to Jupiter's polar upper atmosphere by generating an electric current known as the Io flux tube. A flux tube is basically a concentration of magnetic field lines. The Sun has these between sunspots and is very visible on the Sun because of the charged plasma that flows between them. Io's flux tube causes an aurora trail around Jupiter's poles. This point here is the flux tube from Io striking the upper atmosphere of Jupiter. Aurora are also visible on Io, although they are not just limited to the poles. The different colors represent the different particles being ionized. Green is sodium, red is oxygen, and blue from sulphur.
Since late December, the Tonga High volcano has seen a lot of activity in a series of pretty big eruptions. On the 14th of January, it was spotted erupting again by local scientists. This seemingly huge eruption shot ash 20 kilometers into the atmosphere, creating a pillar which stretched high above their view. But this is all about perspective. The impressive sight from a ground view only appeared like a tiny little pillar from space. The next day, this happened. This eruption, seen by both the GOES West and Himawari 8 geostationary satellites, showed the biggest explosion captured on camera, perhaps ever. Initial reports state this could dwarf even the biggest man-made nuclear explosion, and it's not hard to see why. Just look at how big the ash cloud is. If we overlay it over Europe, we can see that it covers an impressive surface area. Sorry, Luxembourg. Not visible in the satellite images, but detected with radio wave listening instruments, more than 200,000 lightning flashes were counted in the plume. Volcanic lightning is still an ongoing topic of study, and we don't exactly know the processes that cause it due to the difficulty in studying it, but scientists are starting to suspect that positively charged particles come from the eruption itself, as well as interactions with ash in the atmosphere. While the island itself was uninhabited, the islands nearby are. Damage from volcanoes comes in many different forms. The most obvious is the ash cloud. The nearby islands around Tonga have been blanketed, with some news reports saying it looks like a grey moonscape on these islands now, covered by a thin blanket of ash. These before and after satellite images are revealing. Residents here were all told to stay indoors while the ash was falling, as breathing it in can be damaging to the lungs. Ash has settled on fresh water supplies, contaminating them. And what was once a green and colourful place now looks like what would happen if you turn the saturation on an image all the way down. This isn't great for plants initially, as it will block the sun's rays from hitting their leaves, although eventually it will be good for the soil of the islands, as volcanic ash is a natural fertilizer containing many important minerals. However, the lightest ash particles didn't just go horizontally across the atmosphere, but they have also certainly penetrated the stratosphere. Typically, the Earth's troposphere and stratosphere don't mix that well, so if ash gets into the stratosphere, it will stay there and circulate around the globe for months to years. The tiniest ash aerosols contain sulphuric acid, hydrogen sulfide, and hydrochloric acid. Interestingly, this may have a very slight cooling effect on the Earth as a whole, as sulphuric acid, for instance, is known to reflect sunlight back into space. However, the negative consequences are that eventually these particles will come back down into the troposphere, where they will return to the surface in rain droplets, or in other words, acid rain. The next thing you'll notice is this incredible shockwave blasting away from the volcano. The fascinating view is best seen in the infrared, as infrared is better at detecting the slight change in atmospheric temperature caused by the pressure wave. The pressure wave traveled faster than the speed of sound, and it was loud. This video may give you some idea of the scale of this shockwave as it passed by an island 65 kilometers away.
Holy sh!
To be honest, we can be grateful that everyone's eardrums didn't rupture. However, there have been reports that windows from residences were blasted out by the shockwave. This pressure wave is believed to have traveled around the world at least 4 times, as detected by weather stations in various countries. Across the US, the shockwave wasn't audible, but the effects could be seen in the slight fluctuations in air pressure as it passed over the country. However, the shockwave was heard in places as far away as New Zealand and Australia, even in Alaska. Generally speaking, underwater volcanic eruptions don't cause tsunamis, but simply due to the scale and sudden nature of this one explosion, it did in fact cause a tsunami, although not a very big one in the end. It was still enough to do some damage across the Pacific, however, to coastal regions facing the eruption. When news that a tsunami was possible, boats and ships were put out to sea to face the wave head-on. As tsunamis reach shore, the amplitude of the wave increases, causing it to look much more visible compared to a tsunami far out at sea, which is why the wave looks so big here. These boats are not too far from shore. The last damage I want to examine is to the volcanic island itself. This island is very new. It's only been in existence since 2014. This is because it lies right on the Pacific and Indo-Australian convergent plate boundary, a tectonically active area. Before 2014, it consisted of 2 mostly submerged islands, with the caldera around 150 meters below sea level in between them. It had since erupted, filling the gap, merging the 2 islands. As a result, it has actually been studied by NASA themselves to better understand how water impacts volcanoes, as there are plenty of old volcanoes on Mars that would have also been surrounded by water. Scientists wanted to track the erosion of this newly formed island, formed in the ocean, to see if there are similarities to the erosion patterns on the literal fields of Martian volcanoes, potentially providing additional evidence that certain Martian volcanoes were once also surrounded by oceans of water. It's also interesting for scientists to be able to tell exactly how analogous planets like Earth and Mars really are, despite their differences. As for Hunga Tonga Hunga Haipai, the ash building the island initially was easily washed away by the lapping seawater, like a sandcastle disappearing to the tide. However, after about 6 months, the erosion stopped as the ash and seawater actually combined to produce a harder, more resistant type of rock. And had volcanic activity stopped for good, Hunga Tonga Hunga Haipai would probably have remained a small island for many years to come. However, the force of the January 15th eruption has absolutely decimated the island. What was one stretch of land only last year is now 2 separate islands again, with the caldera disappearing back below the sea level. However, just imagine if one day Earth was to meet a similar fate to Mars and its sea was completely drained. What now looks like a tiny little island to us would still look like a towering 2,000-meter high mountain from the seafloor. While volcanoes on our own planet are pretty intimidating, we can take solace in the fact that an explosion of this size could have been a lot worse for us humans. Moreover, this particular island will continue to be examined by NASA for years yet, helping us understand our own planet, but also our neighbors in the solar system. And why should we care? Well, volcanic activity at this scale can have global impacts. And by studying their interactions with the atmosphere and oceans, we not only can help predict our futures, but understand the past on planets like Mars. Enceladus. Perhaps one of the most intriguing objects in the entire solar system. And yet it is only the 6th largest moon of Saturn, and in natural light, it looks very unassuming. However, there's a lot more to Enceladus than meets the eye. It's an active, icy world with jets of water vapor pouring out from its southern hemisphere. Thanks to the remarkable Cassini mission, we have studied and observed Enceladus in exquisite detail, and perhaps know more about it than some of the closer and bigger Jovian moons. However, although we've seen a lot from the outside, it's the inside of the moon that still holds so many mysteries. I'm Alex McColgan and you're watching Astrum, and together we will explore some of the most fascinating details of Enceladus, piecing together photos and data from a variety of missions to find out almost everything you could want to know about this special moon. So stick with me on this journey of discovery. Let's first of all discuss where Enceladus fits into our solar system. Enceladus is currently Saturn's 14th closest moon. I say currently, as Saturn has some tiny moonlets hidden in its rings that may or may not be classified as moons in the future. It is the 2nd closest major moon though, second only to Mimas. That means that its orbit takes it just outside of Saturn's major rings. Its orbit follows the planes of the rings very precisely, and it only takes 33 hours to orbit Saturn once. Interestingly, it is in a 2-1 orbital resonance with Dione, Saturn's 4th closest major moon. In other words, it orbits twice around Saturn in the time Dione orbits once. This orbital resonance is believed to prevent Enceladus's orbit from ever becoming perfectly circular, which causes Enceladus to undergo tidal deformation. This is significant, as these tidal forces heat up Enceladus's core. You see, as far as we can tell, Enceladus's surface is predominantly made of clean water, certainly with little to no rocks or much else there. Because Saturn is situated so far away from the Sun, it means the outer layer of water on Enceladus has frozen over. Enceladus is essentially a frozen ocean world, a giant ball of water ice. Because it is free from other materials on the surface, the Moon is one of the whitest objects in the solar system, with a bond albedo of 0.81, which is pretty much as high as snow. As such, it is one of the coldest satellites of Saturn, with a noon temperature of -200 degrees Celsius, as the white color of its surface reflects a large percentage of the sunlight reaching it back into space. However, about 30 to 40 kilometers down under the surface of Enceladus, pressures start building and heat energy generated from the tidal deformation of its orbit has increased the temperature of the water ice to the point where the water at this depth can exist in a liquid form. It could well be that there is an entire mantle or a global ocean of water that the ice crust is resting upon, very much like the magma mantle that our rocky crust on Earth rests upon. At the very least, scientists expect there to be a huge pocket of water under the moon's south pole. How do we know this? Well, the most obvious indication are the huge plumes of water being ejected from the cracks in the crust, something referred to as water or cryovolcanism. These jets are really active, consistently blasting around 250 kilograms of water into space every second at speeds exceeding 2,000 kilometers per hour. This is powerful enough that most of the water vapor particles escape Enceladus's weak gravity, and they end up in orbit around Saturn, forming Saturn's E-ring. This ring around Saturn is very diffuse, and so isn't really visible unless it is backlit by the sun. From this angle, the light shining through the water particles make the ring appear exceptionally blue. In fact, this ring is considered the bluest object in the solar system, even more so than Neptune due to the ring's uniformity. The E-ring is Saturn's second outermost ring, and it is 2,000 kilometers wide. Its shape is also heavily influenced by the orbit of Enceladus. Enceladus's plumes create tendril shapes in the rings as more material erupts out of it. However, these sections of the ring tend to smooth off as Enceladus moves further away along its orbit. During the course of Cassini's mission, Cassini was able to pass through these plumes to detect the substances being ejected from them. Cassini wasn't designed with this in mind. Scientists didn't know about the plumes until Cassini got there. However, Cassini was equipped with an instrument called the Cosmic Dust Analyzer, designed to detect what the tiny dust grains in orbit around Saturn are made of, and it was able to use it for Enceladus's plumes too. As it wasn't specifically designed with this in mind, it might not have given us the full picture of what's in these particles, but while water was the predominant substance detected, amino acids, carbon dioxide, nitrogen, and methane were also found. Amino acids are significant as they are the building blocks of life and can be found around the thermal vents at the bottom of Earth's oceans. Does this mean Enceladus has thermal vents of its own? And if so, do they have ecosystems of life around them? While evidence for an underground ocean is abundant, scientists still aren't completely sure about Enceladus's internal structure. At some points in the past, scientists believed that Enceladus was water all the way through. However, data from Cassini suggests that Enceladus's mass is in fact greater than previously thought, meaning it must have some amounts of iron or silicate material in its core. Scientists are starting to lean towards the theory that the internal structure is differentiated, meaning it's a celestial body with defined layers within it. An object of this size really doesn't have to be differentiated. In fact, it's so small at only about 500 kilometers across that it is right on the borderline of being in hydrostatic equilibrium, or in other words, being rounded by its own gravity. There are a number of objects out there of similar or smaller sizes that are not in hydrostatic equilibrium, like Neptune's Proteus. In any case, assuming it does have a differentiated interior, this core is likely to be predominantly rocky. This is important, as thermal vents in Enceladus's water ocean would have to come from a rocky core. A rocky ocean floor would also provide nutrients and minerals essential for what we believe life would need to form and evolve. Thermal activity clearly does exist due to the way Enceladus has plumes in the first place, and the amino acids detected in the plumes suggest a rocky core. As Cassini passed over Enceladus, it also mapped out the thermal emissions from the moon. It turned out that the jets line up with what has come to be known as Enceladus's tiger stripes. These are large depressions, roughly 130 kilometers long, 2 kilometers wide, and 500 meters deep. It is believed that these are tectonic fractures in the moon's icy crust. What is really interesting about the surface features of Enceladus is that there are virtually no impact craters at all over the southern hemisphere, and not many anywhere else. This implies that Enceladus' surface is very young, as while it does have a thin atmosphere made up from the ejected water from the plumes, this isn't nearly enough to burn up asteroids before they hit the surface. Some water from the plumes obviously settles again on the surface, which smooths it off over time. This is another reason why Enceladus is so round for such a small celestial body. In fact, apart from the tectonic fractures and few craters, Enceladus' topographical variation is really quite minimal. There are no mountain ranges to speak of, although there is what you might call a rough terrain around the South Pole if you zoom in far enough. This is perhaps the highest resolution image we have of its surface, and as you can see, it really does appear like a giant glacier. It's interesting to note that even in this small view, there are some smooth sections of ice, but also jagged regions. Over the North Pole, the clear difference is the number of craters present there. While there are tectonic fractures here too, there are no plumes on this side of the moon, so the surface here is clearly a lot older than around the South Pole, which is why it has more of a cratered surface. As Cassini flew through the plumes around the South Pole, it also took the opportunity to image the surface closely around the tiger stripes. The surface here is pretty incredible, unlike anything you would have seen on Earth. It's like the surface has been folded, squashed, and shifted around, leaving these remarkable fracture lines and formations in the surface ice. The fact that Cassini was able to get so close to Enceladus is a feat in and of itself. It's fantastic that we can have such a close-up view of something so far away. Unfortunately though, since the Cassini mission has ended, we no longer have anything in orbit around Saturn that can study Enceladus further. There have been plenty of mission proposals in the past, but all of them were cancelled before they came to fruition. What would be incredible is a probe that could either make its way into Enceladus' ocean somehow, or at the very least, search the plumes for signs of life. There is already a mission called Dragonfly going to the nearby moon of Titan, however this won't have anything to do with Enceladus. So, although a couple of mission proposals are currently under review to go there, that means we are unfortunately still a couple of decades away at least, which is a shame because who knows what secrets lie in wait under that crust. So there we have it, a look at the intriguing little moon of Enceladus. Triton is an exceptionally unusual, although often forgotten moon. It has so many unique characteristics, it makes it one of the most interesting objects in the solar system. But because it is the largest moon of Neptune, the planet furthest away from us, it also means that we have only visited it once. Very briefly, as Voyager 2 flew by, all the way back in 1989, 30 years ago. But what did the visit reveal, and what have we found out about it since? I'm Alex McColgan, and you're watching Astrum, and together we will find out everything there is to know about the fascinating world of Triton. First of all, let's discuss where Triton fits into our solar system and its local system. Triton is one of 14 known moons of Neptune. 7 of these moons are regular moons, or in other words, moons that orbit along Neptune's ecliptic with very circular orbits, or orbits with very low eccentricity. After these inner regular moons, we get to the irregular moons, the first of which is Triton. An irregular moon is a moon that follows an inclined, eccentric, and often retrograde orbit. This by itself is already where Triton is set apart from any other spherical moon in the solar system. It has an irregular orbit. Triton orbits clockwise around Neptune, as Neptune rotates counterclockwise. And Triton orbits at a 130-degree angle to the ecliptic of the planet. Although, it should be noted that its orbital eccentricity is close to zero. Its orbit is almost perfectly circular. All other large moons in the solar system are regular moons, orbiting the same direction as the rotation of their parent planet. What this heavily implies is that Triton did not form alongside Neptune, but it is in fact a captured object. Specifically, a captured dwarf planet. No wonder then that it is by far the biggest of Neptune's 14 moons, comprising 99.5% of the mass found in Neptune's orbit. But how big is that in scales we can relate to? Well, it is the second largest moon in relation to its parent planet, second only to Earth and its moon. While it is smaller than our moon, it orbits closer to Neptune than our moon orbits Earth, which means it appears about the same size in the sky. It is the 7th largest moon in the entire solar system, and most interestingly, it is bigger than Pluto. Pluto is often considered the king of the Kuiper Belt, the biggest object that we know of that formed there, until we consider that Triton once ruled that area before Neptune captured it. So, although Triton is a moon of Neptune, it could be said that it is the biggest and most massive Kuiper Belt object. Further evidence for this was found as New Horizons passed Pluto in 2015, suggesting Triton and Pluto share a near identical composition, which supports the theory that they share a common origin. Beyond Triton are 6 other irregular moons, found much further out. They are almost certainly captured objects too, with unusually eccentric orbits that take years to complete. They were probably perturbed into these weird orbits by the gravity of Triton. So, if Triton was a captured object, how did that happen? Objects need to lose momentum to be captured, otherwise they would have enough momentum to escape. Well, we can't know for sure, but the leading theory right now is that Triton was once part of a binary system, perhaps like Pluto and Charon. As Neptune approached Triton and its moon, the gravity from the encounter would have caused the binary system to fall apart, with Triton's moon being slingshot away and Triton losing enough momentum to be captured in orbit around Neptune. I mentioned that Triton shares similar characteristics with Pluto. What exactly does that entail? Well, they both have a predominantly nitrogen ice surface with other ices mixed in, like water and carbon dioxide. It has quite a flat terrain. Its topography never varies by more than a kilometer. Although Voyager 2 did see ridges and troughs, plateaus, and ice plains. What you may find unusual though, is that it has very little in the way of craters. This implies its surface is very young and is constantly being renewed. Like Pluto, it also has some reddish patches, which is thought to be methane having reacted to UV light from the sun, producing what is known as tholins, an organic compound that has a supposedly tar-like consistency. While organic compounds do not mean life is present there, organic compounds are the basic chemicals from which life forms. Life likely couldn't exist on the surface of Triton anyway, as it's far too cold and the sun far too dim to support any life form that we can imagine. But what's interesting is what could be found under Triton's crust. Under Triton's surface is thought to be a rocky and metallic interior, which gives Triton a reasonably high density for a moon at 2 grams per centimeter cubed. Because of this, and also due to the big step up in size from the next biggest moon in the solar system, Titania, it has more mass than all the moons smaller than it in the whole solar system combined. The radioactive decay from the rocky core could be enough to heat and power convection in a subsurface ocean of water, much like what is thought to be under the surfaces of Europa, Enceladus, and some other large moons in the solar system. And just like Europa and Enceladus, cryovolcanism is an active process today on Triton. Liquid water in the mantle erupts onto the surface like lava on Earth. This is the main reason why the surface is so young. It is being actively renewed by liquid water erupting and then freezing on Triton's surface. Some very young lava plains have been identified, sparse and flat regions, yet, interestingly, with a wall that surrounds the plain. This is called a planitia, or in other words, a solidified lava lake. We also can see caldera, which is the collapse found at the center of a cryovolcano, where lava plains formed from. It is thought that the water from these eruptions would have also brought minerals from the underground oceans onto the surface, perhaps even being the source of the tholins and organic matter I mentioned earlier. If this is the case, and organic compounds are found in the subsurface ocean, it means that there's a possibility that conditions are right for life to have been able to form there. We also see long lines permeating over the surface. These are likely faults, caused either by tectonic activity or freeze-thaw weathering processes. If we look at some more of the Voyager 2 images of Triton, we can see the results of some recent eruptions. You'll notice what looks to be dark deposits on the surface, in cone or funnel-like shapes, up to 150 kilometers long. However, these smaller eruptions may not originate from the mantle itself. Voyager 2 spotted some plumes reaching 8 kilometers high, but these are thought to be because of a solid greenhouse effect within the moon's icy crust. Imagine the surface of Triton, consisting of a clear ice, which has settled on dark deposits like tholins. The sun shines through the ice, warming the darker, more absorbent tholins beneath, which sublimes a pocket of ice under the surface. As the ice is sublime, the pressure builds in the air pocket until the surface above the pocket gives way, causing an eruption. This eruption also takes the dark deposits with it, spreading them out over the surface again. If this is the case, a very similar process has been seen on Mars's poles, with carbon dioxide ices and darker deposits under the ice layer. This process can only exist because of one thing: Triton has an atmosphere, although not as thick as scientists were initially expecting. Triton's atmosphere is thin, only 0.014 millibars, about the equivalent of 80 kilometers up on Earth, although, like Pluto, this density varies through seasonal changes. Since Voyager 2's observations, Triton's atmosphere has become denser as the surface has warmed, evaporating a little of the nitrogen ices on the surface. However, when Voyager 2 passed, Triton's atmosphere was still dense enough to support weather up to 8 kilometers above its surface. In this image, you can actually see clouds on Triton. And going back to the image of the plumes, you can see the deposits from the eruptions all end up facing the same direction, due to a prevailing wind in that region of the moon. Like Pluto, Triton's atmosphere is hazy, the cause of which is thought to be hydrocarbons in the atmosphere not yet broken down into tholins by UV light from the sun. The constant depositing of organic compounds through cryovolcanism, ices evaporating and freezing again through seasonal variations, and a weather-rich, active atmosphere makes Triton a very dynamic world, unlike most other moons in the solar system. It is more a dwarf planet than a moon, likely a sibling of the more famous Pluto in the Kuiper belt. All of these factors combined make it one exceptionally unusual moon. And there we have it, everything you could want to know about Triton. Thanks for watching. I was honestly blown away by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrum team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 Patreon member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.